Welcome back. Okay, so we did some very basic linear algebra, as it's called. So before continuing with the next topic, let's uh, um, let's do this. So why we need all this stuff in electronics? So let's introduce this idea, which we will formalize later. So let's say that as an example we want to record the temperature. Let's call it f as a function of time, temperature in this room. So we can monitor the temperature with a sensor. We will see something like this, maybe, whatever. So this is what we will call later an analog signal, so a continuous variable that we can record somehow. But let's say for the moment that we can collect some samples. Now I draw some samples like this. So these samples occurs at specific time instants. So there is one here, let's say at t0, another one here at t1, another sample at t2, and so on. Generic sample at time instant tn. So we need to store these values. Which values? The values of f of t. So the value at t0 is this one. The value at t1, we have to go here, it's this one. Okay, those are difficult to see, but for instance this one, this value here corresponding to t, let's call it m, this value is f of tm. So we can do the same for the other values. So we have here a list of numbers, list of numbers representing our function of the time, which is our signal of interest. So the idea is that from this list of number we build an n-dimensional vector like this. So we have a list and inside each of those boxes we write those numbers. So let's call it f1, f2, f3, fn. Here we have fm, this value recorded at the time instance tn, and so on. So if we record for a very long time, then this list is going to be very big. So let's say that we can record forever. This list is infinitely long. So we will make an association between those type of lists and vectors in a formal way, so that we can compute something on this kind of things. So this is why we are developing this framework, mathematical framework of vectors. We need a couple of ingredients to be able to do so. So one was this thing of linear algebra we did. The other thing we need are complex numbers, which is the next topic. So complex numbers are numbers which have been invented at a certain point in order to solve this type of equations, so-called polynomial equations. Actually, we may know this type of equation: ax squared plus bx plus c equals 0. This is a quadratic equation. Historically, people were trying to solve the cubic equations, like x cubic plus b x squared plus cx plus d equals 0. And this equation already has a problem, so it's not always possible to find a solution for x. There are also other simple cases, like if we want to write this equation, for instance, x squared plus 1 equals 0, and then we want to find a value for x, then x squared equals minus 1, and then we would like to compute x as the square root of minus 1, which is a number that doesn't exist among the set of the so-called real numbers. It doesn't exist because it's a number that raised to the square should give minus 1. So if x is a positive number, positive multiplied by a positive number gives a positive number. But if x is a negative number, so minus x multiplied by minus x is again a positive number, and this is negative, so we have a problem. So for this reason, there are such kind of numbers which are called complex numbers. We can write in this form: a plus ib, where a and b are real number and I is a new number which is called the imaginary unit, defined to have this property. We never compute this number, so it always remains a symbol I, but we consider that this symbol has this property attached to it, that the square of I is minus 1, which is something that is useful in order to solve these types of equations. So this would be I in this case. So if we go on with this, then we can describe those numbers. So we are speaking now of numbers we can write in this form: z equals a plus ib. So they have two parts. One part is called the real part, so a is the real part and b is the imaginary part. And they are separate, let's say. So they can be thought, the numbers themselves, I mean those z number, complex numbers, themselves, they can be thought as two-dimensional vectors. So this would be the real axis and this would be the imaginary axis. So because they have these two parts, those numbers have a length. So here this thing rho is the length of this imaginary number z equals a plus ib. They also have an angle which is sometimes called phase, phi, and with basic laws of trigonometry, so this vertical part is this one, we can understand that the tangent of this angle phi is b over a. So the ratio between the imaginary and real part of a complex number is the angle of the number, the phase of the number. And similarly, this thing, which is Pythagoras theorem, is saying that this is a rect triangle, this one. So the square of the hypotenuse, this one, is the summation of the square of this cathete plus the square of this other cathete. And therefore, if we want to get rho is just square root of a square plus b square, and this is a and plus ib. So the complex numbers are an extensions of the real numbers that are useful when we try to deal with certain equations that has no solutions in the real number domain. So now we go a little bit further, and then we want to apply this knowledge of complex number in order to define a specific function which is called the complex exponential function. So why do we need this? Because we will see that this function is useful in order to give a geometric description of signals when we think of signals as a huge collection of numbers that we can think like vectors. So more specifically, we will need this complex exponential function in order to define a basis of function that will allow us to define a reference frames of vectors in a big number of dimensions, in which we can represent our signal as a multi-dimensional vector. I know that this passage sometimes it's a little bit abstract and unclear, but we need to concentrate on some pillars, let's say, to digest it. So the first one is the concept of vectors. The second one is the concept of function as a collection of numbers. The third one is we need a basis of a reference frame in order to represent a vector. So to get to this basis concept, we need to pass through this complex exponential function. So we know the normal, let's say, real exponential function, which has this chart, something like this. So, okay. What we maybe don't know is what the complex exponential function is. So instead of writing a to the x, or just not to be confused here, I write a to the y plus ix. So let's try to write a to the z, having in mind a complex number z equals y plus ix, or a plus ib if you prefer. So first passage is that we can simplify this into this by remembering a property of the exponential function. So the exponent Exponential function, when the exponent is the summation, is the product of the individual exponential functions. This guy is the, let's say, normal exponential function. We know. What we maybe don't know is what this thing is. So in order to discover what this thing is, we can play a trick. We can take advantage of a formula which is called the Taylor expansion, or Taylor formula, which is this thing here, which, to make a long story short, tell us that, let's say, not every, but most of the smooth functions, let's say, can be written in a different way if you know the derivatives of the function of interest calculated in a certain specific point that you can choose. So now the exponential function is good for us because you probably know that the derivative of an exponential function is again an exponential function, and then the second derivative, which is the derivative of the first derivative, it's again an exponential function because the first derivative is an exponential function. So all the derivatives of the functions are the same. So it means that we know how to calculate all these kth derivatives here. So the Taylor formula says that once you know these derivatives calculated in a specific point where you know how to calculate, then if you summate all of them multiplied this interval x minus x0 to the k divided by this funny number which is called factorial, and for once the ones who don't know what a factorial is, so let's say that k factorial is 1 by 2 by 3 by 4 by till k. It's a shorthand for this notation. So this thing, because of this Taylor formula, is equal to this. We just copied the argument here for the moment without knowing what it is. But we can calculate the derivatives. So let's try to calculate just the first derivative, so of this guy here. So the derivative d on dx on eix is the exponent ex multiplied I multiplied e to the ix, and we have to calculate it on x equals x0, and we choose to calculate it on x0 equals 0 because we can easily calculate a to the x or to the ix when x is 0, because a to the ix0 when x is 0 is a raised to the I0, which is a to the 0, and whatever is raised to the 0 is 1. So this thing is equal to I, because this guy here is equal to 1 when x0 equals 0. And this thing would be I k for k equals 0. Then we choose x0 equals 0 because we know how to calculate all the derivatives in that point, and therefore this x minus x0 to the k is x to the k, and then we have the k factorial. So if we carefully do this, the first term was I, then x to the k with when k equals 1 is this one, otherwise it becomes 1 and we have these terms. And if we carefully calculate all the terms for every possible values of k, we get all these things here. So now a passage we have to do is to carefully rearrange the term. This thing is a little bit dangerous because rearranging terms of an infinite summation is not always possible, but in this case we can demonstrate, we don't do this, that it is possible. We can put together between round parentheses all terms without the I, so all the real terms, plus I multiplied all the terms with the I, so the imaginary terms. So we split this summation into two summations, one with real terms and the other with only imaginary terms. And if we carefully inspect those two summations here, we can find that these are the Taylor expansion respectively of the cosine function and the sine function, meaning that if we take the Taylor expansion not of the exponential but of the cosine, we get exactly this series of terms, and if we take the Taylor expansion of the sine, we get exactly this thing, and the I is outside as a common factor. So then we discover this formula, which is called the Euler formula. So this is Euler, we discovered this formula, and this is something that we will use into this, let's call it with its name, signal processing, in order to describe signals. It's an ingredient we need, it's not the only thing we need. So now we understand that this exponential function is made of two parts. It's a complex number where the real part is the cosine of x and the imaginary part is the sine of x. So the complex exponential is a complex number with some sort of periodicity, because we know that cosine and sinusoidal functions are periodic, and therefore there is a concept of frequency in this thing, in this complex exponential function. Okay, we have other 10 minutes. So to summarize, we said this basically: complex numbers, real plus imaginary part. Here you have the properties, the basic properties, which relates the two different views as magnitude and phase, which is called polar form, to real and imaginary part, which is called Cartesian form. And here there is a third way of writing a complex number by means of the Euler formula that we kind of, let's say, not really demonstrated right now. So 3 ways of writing complex numbers. Sometimes one form is useful, sometimes another form is useful, sometimes the Euler form is useful. They are all equivalent, mathematically speaking. Again, let's try to say something about these complex numbers. They have some properties. So we associate the complex number to a 2D vector made of a real and an imaginary part. There is this operation which is called conjugation, indicated by a star like this. So we read this Z star or Z conjugate, and this operation by definition produce a number starting from this one without the star, which is the same you have but with an opposite imaginary part. So it's a reflection. If you have a Cartesian set of axes, let's call it real and imaginary, what is called the complex plane, real and imaginary plane. If you draw this, the z number equals a plus ib, this thing is a, this thing is b, and z star is this one, the one having opposite imaginary part. Some property we can demonstrate is that the magnitude, the square of the magnitude of this complex number, the length of the arrow, let's say, can be also expressed as the product of z star by z, which we can also write this way if we want to use this Dirac symbology, and has this meaning again. So the magnitude of A by magnitude of B, if we want to compute this type of inner product between a number ZB and ZZ star, multiplied the cosine of the angle between the two numbers. So this is an extension of the inner product to the domain of the complex numbers, which is something we need in order to speak about signals. And there is also this relation that we can write. So because this thing, we said that it's the equivalent, this thing is the equivalent of this, which is the equivalent of this. We can use it, and then we can understand that the magnitude of this number is 1, but if we have a number z having a different magnitude, then we have to multiply by its magnitude rho. And this is also a different way to see what the complex conjugation is. So if this number is, angle is phi, then this angle here is minus phi, which is what is written here with the minus. So different way to write the same things. Again, sometimes one way is useful more than another one. Okay, so for the moment we stop here. So next time we will try to apply all these notions in order to describe something that we kind of anticipated. So a signal like this one, that here is represented as a function, how can we give a different representation in a form that the collection of all those numbers here represent a vector? So next time we will see this.